So, hello Year 12 and welcome to a video looking at the main ideas in Topic 3 and Topic 4b. They were combined together. It makes sense to do that. Topic 3 is redox, but it's very difficult to talk about redox without looking at Group 7 and the varying oxidation states of the halogens. And so it makes sense to cover these together. Topic 3 and Topic 4b, redox and Group 7. So, having a look at what you should be able to do, know what we mean by the term oxidation number, calculate oxidation numbers of elements in compounds. You do need to be aware of the special oxidation numbers in peroxides and metal hydrides as well. Understand oxidation and reduction in terms of electron transfers, that's from GCSE, and changes in oxidation number for S&P block elements. Understand oxidation and reduction in terms of electron loss or gain, again GCSE. All this is GCSE. Know that oxidizing agents gain electrons because an oxidizing agent oxidizes something else. And so if it oxidizes something else, it is reduced. So an oxidizing agent is reduced, a reducing agent is oxidized. Understand that a disproportionation reaction involves an element in a single species being oxidized and reduced. Oxidation number is a useful concept for classifying reactions as redox and disproportionation. Indicate the oxidation number of an element in a compound or ion using Roman numerals. Writing formula given oxidation numbers. Understand that metals in general form positive ions by loss of electrons with an increase in oxidation number, and non-metals form negative ions by gain of electrons with a decrease in oxidation number. Be able to write ionic half equations and use them to construct full ionic equations. This is the thing that many of my students in particular aren't very good at, writing those half equations and then combining them together. For Topic 4b, we looked at Group 7, the reasons for the trends in melting and boiling points, physical states, and the electronegativity. What's the reasons for those trends? Understand reasons for the trends in reactivity of Group 7 elements down the group. Understand the trend in reactivity of Group 7 elements in terms of the redox reactions with halide ions, followed by the addition of organic solvent. Again, most of that's GCSE, just with the addition of adding cyclohexane or similar. Understand the reactions of halogens with Group 1 and 2, disproportionation with water, disproportionation reactions of chlorine with cold dilute aqueous sodium hydroxide to form bleach, disproportionation reactions of chlorine with hot alkali, and reactions analogous to those specified above. That means bromine and iodine as well. Understand solid Group 1 halides can react with concentrated sulfuric acid, illustrating the trend in reducing ability. Precipitation reactions of the aqueous anions with aqueous silver nitrate, that's GCSE, but now we're adding aqueous ammonia solution, and reacting hydrogen halides with ammonia and with water to make acids. And making predictions about fluorine and astatine and their compounds by knowing halogens. A lot of this is GCSE knowledge, but it is part of the GCSE that many students never bothered to learn properly and have probably forgotten by now. So let's start with electronegativity. What are the two main trends? Well, clearly the first main trend is that electronegativity increases. Why does it do that? Well, electronegativity is all about how much the nucleus of an atom can pull electrons towards itself. So as you go across within the same shell, if you've got a bigger nuclear charge, then it's got more of a pull on the electrons in the same shell. So if we're considering carbon bonding to hydrogen versus nitrogen bonding to hydrogen, then because nitrogen has got a higher nuclear charge and we're talking about electrons in the same shell, the nitrogen has a stronger attraction to it. The second trend is that electronegativity clearly increases up the periodic table. And that is because although as we go down, we end up with more and more positive charges in the nucleus, we've got a much, much bigger distance between the outer electrons. So the electron, for example, of lithium to the nuclear charge compared to the next shell down, sodium, although the charge here in the centre is much larger, there's more electrons shielding that charge. The electron's further from the nucleus, and therefore the electronegativity goes down as you go down. So fluorine is the most electronegative element that forms compounds. And you need to know this. As you go down group 7, reactivity decreases. This is because incoming electron further from nucleus, so there's less attraction. As you go down group 7, the electronegativity decreases. And this is because, again, shared electrons further from the nucleus, less attraction, etc. But as you go down group 7, melting points and boiling points increase. This is because, now from GCSE, you might have said stronger intermolecular forces, but we need to be a bit more specific at A level. And we've got to talk about this temporary dipole. So as the molecules become larger, they have more electrons, so they have larger temporary forces between the molecules. As the intermolecular forces get larger, more energy has to be put in to break the forces. These are London dispersion forces. And you often need to mention London forces if you're going to get the mark on a question like this. So just explaining what London dispersion forces are, they're the fact that the electrons are constantly moving around the nucleus, and it means that you can end up, and if we watch up here, you can end up with all the electrons on one side, and the first thing to happen is that this one generates a slight negative charge and a slight positive charge. Well, once that's happened, that pushes the electrons in this one away, and that means that this one ends up negative. So you end up with two atoms of neon in this case, with a negative charge and a positive charge, and that leads to an overall weak attraction. And here's another example up here. So you've got the electron clouds moving around randomly around the atom, and normally that's not interesting, but when two things come together, these electron clouds harmonize so that you always end up with, for example here, a positive end and a negative end attracting these. They're never negative or never repulsive. They can't be. They can only ever attract, and everything has them. All atoms, everything with electrons has these London dispersion forces. It's just that the larger the molecules, the larger the number of electrons, and therefore the stronger these forces can be. Hence iodine, if we go back here, has much higher melting and boiling points than something small like fluorine. reminding you what oxidation state is, for covalent compounds, the oxidation state is the charge an atom would have if all bonds were ionic. So for ionic compounds, the oxidation state is the charge. But for something like water, well, we know that this is not a real representation, as electrons much closer to the oxygen. The oxygen is far more electronegative. It pulls on those electrons much more strongly than the hydrogen does. So on the right, this is a far more realistic representation. And if we therefore split this molecule up, what we would find is that hydrogen, which initially had 1 electron, has lost it. It is a 1+ charge. The oxygen, which had 6 electrons, now has 8. It is 2-. So this would give us an oxidation state of 1+ for the hydrogens, 2- for the oxygen. It's all about whether the electrons are right in the middle or closer to one atom or another. Here's a similar example with peroxide. Now again, on the left we've got what you might draw at GCSE, dot cross. On the right, again, we've got a more realistic representation where the electrons are much closer to the oxygen than they are to the hydrogen. But in the middle, of course, where it's pulled by 2 oxygens, you can see that the electron pair is right in the middle. So if we split this up, we would see that the hydrogens have a 1+ charge, but each oxygen has got 1, 2, 3, 4, 5, 6, and 2 halves. In other words, it's got 7 electrons. So it has a 1- charge. Okay, so we would say that it would have a 1- oxidation state. You don't really split these up, but the presumption for the oxidation state in a covalent molecule is if you were to split the bonds down the middle, what charge would things have? Few things to remember. Group 1 metals always +1. Group 2 metals always +2. Oxygen is almost always -2 unless it's bonded to another oxygen or it's bonded to fluorine. Hydrogen is usually +1. The exception is a metal hydride like NaH, where it is -1. Fluorine is always -1. Chlorine is usually -1. And the reason for that is if you know your electronegativity, fluorine, then oxygen, then chlorine. Obviously chlorine, the only things it loses electrons to are oxygen or fluorine. Note, any element not in a compound is always 0. So for example, if you've got F2, quite clearly each fluorine has an oxidation number of 0, not -1. And we can use this oxidation state of chromium in CrCl3. We don't know about chromium, but we do know that chlorine is -1, so therefore chromium must be +3. For copper, we don't know about copper, but we do know that fluorine is going to be -1, so copper will be +1. For the chromium in the dichromate ion here, well, we can say that we know each oxygen is going to be 2-, so that's 7 times 2-, which gives us 14-. The overall thing is 2-, so that means the chromiums must be 12+. So each chromium must therefore be 6+. And you could do that as an equation if you wanted. You've got to be able to recognise a redox reaction. Which one of these is redox? Well, if we put on the oxidation numbers, we can see sodium is +1, chlorine is -1, hydrogen's a +1, oxygen -2. There's no change in oxidation state, so that is not redox. That is just an acid-base reaction there, with a proton being given from the hydrochloric acid over to the hydroxide. However, the first one, you can see that magnesium has gone from 0 to a +2, chlorine's gone from -1 to -1, so that hasn't changed. Hydrogen +1 to 0, so that is redox. And whenever you're asked to find a redox reaction quickly, look for anything where an element goes into a compound, because that almost certainly will be the redox reaction. Here's a few examples. I'm not going to go through them, but what is the oxidation number? Work out the oxidation number for each of these. Feel free to have a go if you struggle with this. And reminding you of how the namings work. So, for example, up here, MnO2, the manganese is clearly +4, so we write manganese 4 oxide. You do need to know the general trends in the halogens, far more so than at GCSE. You need to know that fluorine is a yellow gas. You need to know that chlorine is a green gas. You need to know that bromine is a brown liquid. And you need to know that iodine is a grey, don't get caught out, solid that turns into a purple vapour. It's really essential that you get your terminology right. The difference between a halogen, for example, astatine 2, where it is diatomic, and a halide, for example, At-. If you use the wrong terminology, many mark schemes will penalise you and dock something. So the halogen is the diatomic element, Ha2. The halide is the ion, Ha-. As it says down here, the spec states you must predict the properties of astatine and fluorine based on the trends you know for chlorine, bromine and iodine. This is why things get a bit more complicated, because at GCSE we just say group 7 get less reactive as you go down. But now we've actually got to be a bit more specific about what we mean there. Less reactive at what? Or more reactive at what? So oxidizing agents are electron acceptors. A halogen that is a strong oxidizing agent will displace a halogen that has a lower oxidizing power from one of its compounds. Oxidizing strength decreases down the group. Okay, so a fluorine molecule picking up 2 electrons and forming 2 fluoride ions, that's easy. But iodine picking up 2 electrons going to 2 iodides, that's much harder. So oxidizing strength decreases down the group, but the reducing strength increases down the group. So if we're talking about the other thing, 2 fluorides giving up 2 electrons to form fluorine, that's very hard. But 2 iodides losing 2 electrons to form iodine, that's much easier. So iodide is a much stronger reductant than fluoride. Okay, so you've also got to be able to discuss whether or not, for example here, fluorine would be able to take electrons from iodine, and of course it would. You know that from GCSE. So this is what you need to get in your mind. As you go down group 7, the ability of a halogen to accept electrons decreases. This is because, you know, lower electronegativity, weaker attraction to incoming electron, ... As you go down group 7, the ability of a halogen to displace another halide from a compound decreases. This is because, see above, okay? If they're fighting over electrons, the higher up group 7, the more it can attract the electrons. This is an experiment that we do with Year 9 students. I'm sure you did it at GCSE as well. Reacting chlorine solutions, bromine solution and iodine solution with bromine, chlorine and iodine water, and for example chlorine and potassium chloride. Well, this you wouldn't see anything happen. this yellow solution, no reaction, brown solution, no reaction. Potassium bromide and chlorine, the colourless and colour solution, would generate a yellow solution. That's because you've generated bromine, and many of you really struggle to do this in your mind. Bromine and potassium bromide, iodine and potassium bromide, no reaction. Potassium iodine and chlorine would generate a brown solution. Why? Because chlorine is able to displace iodine, generating iodine water, which is brown. Potassium iodide, which is yellow, and bromine, which is yellow-orange, would generate a much darker brown solution because bromine displaces the iodine. So those are the three where you see a darkening. Now, you should know that from GCSE, but the new bit here is, of course, if you add an organic solvent, you should see, this is the one that you should know, purple indicating the presence of iodine. You form a purple layer, and down here as well. Chlorine just gives a colourless layer in the organic solvent. You may not have seen it, but actually leave it long enough, bromine will generate a slight yellow colour to the upper layer. So if you see that the organic solvent has gone yellow, that indicates bromine. And this is of course used to distinguish a concentrated bromine solution, which would be orange, from a dilute iodine solution, which would also be orange. So this would tell the difference between concentrated bromine and dilute iodine. Another reaction that was very similar to some tests you did at GCSE is reacting these things with silver nitrate solution. So if you react to fluoride, chloride, bromide, iodide with silver nitrate solution, what would you see? And also you did carbonate as well. And what you would have seen, you didn't do this, but fluoride does not actually give a precipitate with silver nitrate. The chloride, you should know this from GCSE, gives a white precipitate. Bromide gives a cream precipitate, iodide gives a pale yellow precipitate, and these are the appropriate ionic equations that you should know from GCSE. Something that they do mention quite a lot is why do we need to acidify this? And that's because silver will react with the carbonate ion to give silver carbonate precipitate, which is also a pale yellow / cream colour. So we acidify it because if there's any carbonate ions and we add protons, that will give us carbon dioxide gas and water. So the acid will remove any carbonate ions and prevent that from ruining our experiment. And that's why if we've added acid and got rid of the carbonate, then there's no precipitate because there's nothing to react with the silver ions. But again, as with the first experiment, we just added a little extra step, which was add the organic solvent, the cyclohexane. With this one, we're adding an extra step. We react with ammonia, either dilute or concentrated. Now, chloride will actually redissolve in both dilute and concentrated ammonia. Okay. Bromide will only redissolve in concentrated ammonia, but it won't redissolve in dilute ammonia. So I'm going to write redissolves in both. Just in case you think it only redissolves in dilute, it doesn't, it redissolves in both. Bromide only dissolves in conch, and iodide does not dissolve in either. And of course this again can be used to help differentiate between them if the colours look similar. So yes, while in a perfect situation you can tell the difference between white and cream and pale yellow, in reality it's quite difficult, and so the ammonia will help distinguish for you. It may be that this equation comes up. You wouldn't be asked to generate it, and you will look at this sort of thing far more in year 13, but the silver bromide solid, for example, and 2 ammonia molecules forms a complex where you've got an Ag plus ion with 2 ammonias bound to it. Obviously the nitrogen, being the negative bit with the lone pair, points towards the silver, and that is the positive ion floating around in solution, and you've also got the Br minus floating around. So just in case that ever comes up, just so you've seen it. Effect of light on silver halides, you don't need to know much, but the precipitates except silver iodide darken in sunlight, forming silver. This reaction is used in photography to form the dark bits on photographic film. So silver chloride forming silver and chlorine, and of course the same for bromide. So silver bromide forming silver and bromine. But as it says there, except silver iodide. This was the one that gave people a lot of problems, and it comes up again and again. So do make sure you understand this. Reacting the various different salts with concentrated sulfuric acid. We did this in the fume hood. It generates a huge mix of interesting observations. If I were you, I would pause the video and see if you can remember what each observation indicates. Well, hopefully you remember that the steamy fumes indicate a hydrogen halide. You know that the red fumes would indicate bromine gas. You could call them brown if you wanted. The colourless fumes, that's sulfur dioxide gas. You might be told that that's a sort of choking gas, sulfur dioxide, because of course it forms sulfuric acid when it reaches the wet parts of your lungs. Purple fumes is clearly iodine. A black or a grey solid is clearly iodine. Colourless fumes again. The yellow solid is sulfur, and the rotten or the eggy smelling gas, that's hydrogen sulfide. So how many of those did you get right? For all hydrogen halides, there is a redox reaction in which the halide salt reacts with concentrated sulfuric acid. This is the only time you're allowed to use liquid for an acid, is concentrated sulfuric acid. H2SO4 liquid, that does mean extremely concentrated. And this forms the hydrogen, the sodium hydrogen sulfate, okay? In many equations or in many mark schemes you will see allow Na2SO4 aqueous, but technically that's not correct. So you form the sodium hydrogen sulfate or the potassium hydrogen sulfate and the hydrogen halide there. And this happens with all of them. Is this a redox reaction? Well, no, it's not a redox reaction. The numbers of every element at the start and end, the oxidation numbers are the same, so that's not redox. That is just simply an acid base. For bromide, you get this acid-base reaction, but then it goes further. You remember that you generate sulfur dioxide, and you generate bromine, and then you've got to go and balance this equation. This one isn't too bad. If you've got 2 bromines there, then you must have 2 hydrogen bromides, 1 sulfur there, one sulfur there. You've got 4 oxygens, 2 there, so you must have 2 H2O, and therefore 4 hydrogens on the right hand side, 4 hydrogens on the left hand side. Everything is good to go. So 2 HBr gas plus H2SO4 liquid goes to Br2 gas plus SO2 gas plus 2 H2O. Now that is a redox reaction. The sulfur's gone from +6 to +4. The bromide has gone from -1 up to bromine at 0. So you might also be asked to write the oxidation half equation from something like this. 2 bromides becoming bromine, releasing electrons, and sulfuric acid plus some extra protons generating sulfur dioxide and hydrogen. And we'll have a look at those a bit later. So we've got firstly sulfuric acid acting as an acid, then the sulfuric acid is acting as an oxidizing agent, and as it says, the sodium bromide is a moderate reducing agent, so it can reduce the sulfur from +6 down to +4. With iodide it's even more exciting. You have that acid-base reaction at the start, then you've got the redox reaction that we just saw with the bromine, but then you've got a further 2 reactions here where you're generating both sulfur and hydrogen sulfide. And here it does become a little bit easier to start using oxidation numbers. So we can see on the left that this is -1 going up to 0. So that's going +1, while the sulfur here is going from 6 +6 down to 0, so that is going -6. And because these have to be balanced, that means we need 6 iodides being oxidized for a single sulfur being reduced. So if we've got 6 hydrogen iodides, we must have 3 I2. We've got sulfur, we've got 6, 7, 8 of those. We've got 4 oxygens, and that fits quite nicely for H2O. You can do the similar thing here by again realizing that iodine going from -1 to 0 has to be balanced by sulfur going from +6 to -2, and you can use that to help you balance the redox equation, and that's what you get. So sorry that part of it's fallen off, but that is 6 HI there and 8 HI there. Again, the oxidation and reduction half equations. Again, note that the sulfuric acid plays the role of acid in the first step, producing hydrogen iodide, and then it acts as an oxidizing agent in the next 3 steps. Why can it do this? Well, it's not that the sulfuric acid is an any stronger oxidizing agent, it's that the iodine is a much stronger reducing agent, or sorry, the iodide is a much stronger reducing agent. It can reduce sulfur all the way down to -2, and the sulfuric acid can oxidize the iodine. So this is a sort of question that students really struggle with. Write a half equation to show the formation of SO2 from H2SO4. So the first thing we know is that H2SO4 is forming SO2. But we've got to account for the extra oxygens. So we've got 4 oxygens here, we've only got 2 oxygens here. Now, to account for the others, we can use water, so 2 H2O here. If we've got 4 hydrogens over here, we need 4 on the left. Well, we've only got 2 from the sulfuric acid. Where do the other 2 come from? Well, that must be 2 protons. We use protons to balance the hydrogens. And finally, we need to make sure the charge is balanced. Our products clearly are neutral charge. So our reactants need to be neutral charge. We've got 2 positives, so we need 2 electrons as well. Hence, write an overall equation for the reaction of bromide ions with sulfuric acid. Well, we've got 2 electrons here. They balance neatly with the 2 electrons there, so we don't need to do any complicated multiplications. So we can just add the 2 equations together. So 2H plus H2SO4 plus 2 electrons plus 2 bromides goes to bromine plus 2 electrons plus SO2 plus 2H2O, and then cancel out the electrons, and we have the equation that we saw a couple of slides ago. Deduce the role of the Br minus ions. Well, they are losing electrons, so they are oxidized, so they are reducing agents. Okay, you can have a look at the other questions if you wish. As well as reactions of the halides plus acid, we look at the halogens plus alkali. So do again make sure that you are using the terminology correctly. We're reacting the halides with acid, we've just seen that, but here we're reacting the halogens with alkali. So hopefully you remember that when you add a halogen to cold sodium hydroxide, you get the chloride and you get the chlorate one. And having a look at the redox numbers, we can see that that must be 2. That's quite easy to balance the normal way, but you could have balanced it using redox. So the chlorine and the hydroxide, cold hydroxide, sodium chloride, sodium chlorate 1, and water. What's the use of this? Well, this mix actually is bleach, and it's used to kill or disinfect. It kills bacteria, and obviously very useful. You get the same reaction with bromine and iodine. Okay, with hot sodium hydroxide, you have a very similar reaction. You form the halide, but you also form the halate 5. And again, this is knowledge that many students haven't bothered to learn properly yet. When it comes to balancing this equation, it's fairly straightforward. Again, this is probably easier to do using redox. Iodine going from oxidation state 0 to -1, that's going down 1, going from 0 up to +5 in the halate 5, so that's going up 5. So therefore, to make these balance, you need to have 5 times as many of these as you do of these. So presume you've got 1 of those and 5 of those. We can see you've got 6 iodines, 3 I2. You can see you've got 6 sodiums, 6 NaOH. We've got 6 oxygens on the left, 3 here, so we must have 3 waters, 6 hydrogens, 6 hydrogens. So proving that's redox, it is redox, balancing that equation. The halogen goes to a higher oxidation state of +5, and we can use the changes in oxidation state to help us balance the equation. There we go. If we wanted to look at the ionic equation here, well, looking for things that are the same on both sides. Clearly, the sodium ions are unchanged, but the rest of it is there. So 3 iodines, 6 hydroxides, 5 iodides, an iodate, and 3 waters. You can use your normal ionic equations that you saw last week to help you with that, or 2 weeks ago I should say, or before Easter. Couple more fiddly bits at the end. If you want to make, for example, HCl from NaCl, how do you do it? Well, you can use any acid, that's not a problem. But if you wanted to make HBr from NaBr, well, here you obviously couldn't use sulfuric acid, and many other acids will also reduce your hydrogen halide. Sorry, oxidize your hydrogen halide by being reduced, because acids are slight oxidizing agents. You need something that is an acid but is not an oxidizing agent, and phosphoric acid is the most obvious choice. Phosphoric acid is not an oxidizing agent, therefore you only get the acid-base reaction. As before, as with sulfuric acid, where you only displace one of the hydrogens, here we don't end up with sodium phosphate, we end up with sodium dihydrogen phosphate when we react these two things together, releasing HCl, which, as you should know, makes steamy fumes. Why is it steamy? Well, that's because it sucks in water from the atmosphere, creating water droplets around it and therefore looking like steam condensing. And on that note, hydrogen halides are so soluble that if you have a tube of hydrogen halide, then the water, it would dissolve so rapidly into the water that the water would quickly rise up the tube. What does it form? You should know this. It forms H plus and Cl minus, but we're A-level now. There is no such thing actually as H plus AQ. The hydrogen, the proton, is unstable by itself. What you actually get is you get what's called the hydroxonium ion, where the oxygen is bonded to 3 hydrogens like that. It's used one of its lone pairs, sorry, because that was H plus, it's used one of its lone pairs to form a new bond, and the whole thing is positive H3O plus. Okay. All the hydrogen halides react readily with ammonia to give the white smoke of the ammonium halide. Again, white smoke here, highlighting the difference between steamy fumes and smoky fumes. It's important you know the difference. We can use ammonia to identify a hydrogen halide. We can't tell which one it is, but we can tell that we formed a hydrogen halide. Finally, let's have a look at this. Manganese oxide ion reacts with iron 2 ions in the presence of an acid to produce manganese 2 ions and iron 3. Write a half equation for oxidation, write a half equation for reduction, and combine the two to deduce the overall reaction. Okay, so the first one is that manganate is forming manganese 2 plus. So we ask ourselves, well, what's happening to the oxygens? Well, as the rule says, we use water to balance the oxygens. We've got lots of hydrogens on this side. How do we account for that? Well, we must use protons. That's the rule. We use protons to balance the hydrogens. And finally, we need to make sure that the charge is balanced. Our products have got an overall charge of 2 plus. Our reactants have a charge of 7 plus here. So therefore we need 5 electrons to make both sides balance. The other equation is much easier. It's iron 2 plus becoming iron 3 plus. We need to balance that, so that must involve an electron there. We've got to make these balance. We've got 5 electrons here. We've only got 1 here. So 5 of those, 5 of those, 5 electrons. Now they balance. Now we can add them together. 8H plus MnO4 minus plus 5 electrons plus 5 iron, 2 ions, going to manganese 2 plus 4 waters plus 5 Fe3 plus 5 electrons, and of course we can cancel out the electrons to give our final ionic equation. Okay, I hope that was useful. A whistle-stop tour of Redox and Group 7 Chemistry. As usual, there's a set of multiple choice questions for you to download, to attempt and to enter into the quiz. I'm giving you less time to do this because so many of you are leaving it to last minute, and I really do need to do these videos over the weekend so I can be good to go on Monday. So I'm only going to give you until Saturday to do these questions. Okay, that means I can do the videos on Sunday for next week. Have a nice week until then. See you later.